So now as we begin Module 7, this is going to be broken into two different sections, Module 7.1 and Module 7.2. Module 7.1 is going to be your Exam 1. And I would ask you to please go back to your overview video and to the video and PDF that I've uploaded under Module 7.1 for details about Exam number 1. So as we move on to Module 7.2, this is where we're going to consider two-dimensional steady-state conduction. We're doing this by briefly reviewing alternative approaches to determining temperatures and heat rates, and this relates to section 4.1 in your textbook there. We're also going to cover the topics in 4.2 and 4.3 sections in your textbook as well. Where in section 4.2, we're going to consider some of the mathematical issues that are associated with obtaining this exact solution. In 4.3, we're going to present some complications of existing exact solutions for a variety of different simple geometries. So within this module here, we're going to have a look at alternative approaches to determining our temperatures and heat rates. Then we're going to take a look at the separation of variables, the conduction shape factor, and then also the dimensionless conduction heat rate. So again, this relates to Chapter 3, Sections 4.1 through 4.3, whereas Chapter 3, Sections 4.4 and 4.5 are going to be a supplemental reading assignment for you guys to cover that material in the textbook. So as we look at Module 7.2, we're going to be covering the topics of two-dimensional conduction. This relates back to Chapter 4 in your textbook. We're taking a look at shape factors, dimensionless conduction heat rates. So within this module here, the objectives are to go over the heat equation and the methods of solution, and we're going to take a look at the conduction shape factor, and we're also going to take a look at the dimensionless conduction heat rate. Now, just a reminder, sections 4.4 and 4.5 in your textbook are dealing with the topic of numerical finite difference methods and finite element methods as well there. So this is something that's a review section for you guys that I want you to read on your own, separate from this lecture here. So we're just going to be talking about in this lecture here 4.1 through 4.3, whereas 4.4 and 4.5 are your reading assignment to cover this material there. So within this module, what we're going to do is go through some of the theory, talk about some key equations, different applications, and some problem-solving techniques going through my hand solutions. So as we begin Chapter 4, two-dimensional conduction, we're going to take a look at shape factors and dimensionless conduction heat rates right here. And this relates back again to sections 4.1, 4.2, and 4.3 in your textbook. So the first thing we want to take a look at here is some general considerations right here as we start Chapter 4. So within this here, the first topic we're going to take a look at here is two-dimensional conduction. So within two-dimensional conduction, this is temperature distribution is going to be characterized by two spatial coordinates right here. So for example, right here, we have temperature by two spatial coordinates right here. So we have T of x comma y. So rather than just one that we've dealt with before in 1D, now we're looking at two-dimensional right here. And the simplest way to look at this is a Cartesian coordinate system, our standard x and y coordinate system right there. So that's where we have T of x comma y. Now the same thing can be said now for our heat flux. So this heat flux vector is going to be characterized by two directional components as well. So for example, right here, we might have our heat flux in the x direction and our heat flux in the y direction, denoted here by qx double prime and qy double prime right there for our heat rate in both of those two directions. Or sorry, heat flux in both those two directions. So shown in this diagram below, what we have here is heat transfer in a long prismatic solid with two isothermal surfaces and two insulated surfaces right there. So now we can take a look at this right now and we can see, okay, there's our insulated surface right there. There's our insulated surface right there. So those are our two insulated surfaces right there. And the thing that we want to note about this is the shape of the line. So the shape of the lines of constant temperature are isotherms right there. So we can take a look. There's our isotherms right there. There's the line that we're talking about right there. And we can also talk about the shape of the lines of our heat flow, or our adiabats right here. So where's our heat flow lines? So these are our heat flow lines right there coming up like this here. So the thing we want to consider here is, what we want to ask ourselves is, what equations, what theory, what can we use to determine the relationship, to relate our isotherms and our heat flow? So what we can see for that relationship up in our diagram above right here, so this is our isotherm right there. This is our curve right here for our isotherm right there. What we can see is our heat flow coming off of this, or our heat flux right there. Our Q double dot right there is coming off. And what is this doing right here? Well, this is coming off at 90 degrees. So at any point, this is coming up at 90 degrees to the isotherm. So there's our relationship right there between those, is at 90 degrees. Now, again, we're talking about doing this in two directional components. So this is the same as any of the other courses you've taken, even back to statics and dynamics courses, where if we have a vector term in terms of two variables, or x and y in this case here, we're going to break it down and look at it in terms of those individual components. So that's the same thing they're going to want to do here, is we can say, well, yes, we have this here and it's 90 degrees to our isotherm, but we really want to look at this in terms terms of, we can see our unit vectors right there, our qx and our qy right there. And we break that down, we can do out our geometry, we can do our trigonometry right there, figure out our angles, figure out the lengths, the magnitudes, all that information back from breaking this down right here in terms of its individual components. So next I want to take a look at our heat equation and our method of solution right here. So with this right here, let's assume we have, again, a steady state 2D, so now we're dealing with two-dimensional conduction right here, and this is going to be in a rectangular domain, so that's our simple XY coordinate system right there. We're also going to have a constant thermal conductivity, so there's our K value right there, and heat generation. So with all that, this is our heat equation. Our heat equation for this right here, when we have that heat generation and constant thermal conductivity right here, we have this relationship which stems from our 4.3 in our textbook there. So we have our delta squared T over delta X squared. So we have our partial of temperature with respect to our X position plus our delta squared T over delta Y squared. So now this is with our other direction here. So there's our X and our Y components right there for that 2 dimensions right there. Plus our Q dot right there in our X and our Y right there over our thermal conductivity K right there. So this is our heat equation now for this case. Remember that our Q dot is our rate of energy generation right there. So this is a Q dot right there with respect to X and Y. So now we can talk about the second part of this, our actual solution methods right here. So let's now talk about this exact / analytical solution method right here, where we're talking about first, we go to our section 4.2 in our textbook right here, this separation of variables. This relates back to our calculus, and we've seen this in a couple other engineering courses as well. Now, this is limited to simple geometries and boundary conditions. So that is one thing we have to pay attention to. Are we dealing with a simple geometry right here in order to be able to do out these exact analytical solutions right there? So if we're not dealing with a simple geometry, this may not be possible for us to utilize the separation of variables that we discussed in section 4.2. Next, what we're going to do is take a look at the approximate or graphical solution right there. So this is for the case right here for flux plotting right here, where we have that Q dot is equal to 0. Now, referencing back to our textbook, this goes back to section 4S1 in our textbook right there. So this is of limited value for quantitative considerations, but this is great for a quick aid to establishing a physical insights for something like this. So if you're just looking for a quick and dirty, okay, about where are we with this solution right here, this is where this approximate or graphical solution at least gets you in the ballpark for their answer right there, but it's not great if you really want a more exact, precise solution right there. Last, what we're going to talk about here is our approximate numerical finite difference or finite element or boundary element method right here. So this is very, very useful approach for any adaptable to any level of complexity here. If we're not dealing with a simple geometry and we need something that's a little bit better than an approximate graphical solution right there, it might not be quite the same as an exact solution, but as we change our mesh size, as we change all of our parameters right here, and we add more and more things in, we can get it closer and closer to a more exact solution. It won't be completely exact, but it'll be a good approximation, much better than this approximate or graphical solution right here. Now, there's different types of software that we can use. For some of these, we can use SolidWorks and do some FEA in that. There's also COMSOL. This is a great one. We can code some of this ourselves in Python. ANSYS is another one as well that we can use all these different types of numerical solvers in order to do this out. So this is something to consider, again, for some of these more complex geometries and even just a more complex problem with more boundary conditions than we can really do out by hand with an exact analytical solution. So the next topic I want to discuss is our conduction shape factor, our S value right here. So now if we're dealing with 2 and even 3-dimensional heat transfer problems, and we're dealing with a medium bounded by 2 isothermal surfaces at temperatures of T1 and T2, this can maybe represented in terms of this conduction shape factor S right here. So this relates back to a governing equation that we see in our textbook in chapter 4, which is equation 4.20 right there. So this says that our Q right here is equal to this shape factor, this conduction shape factor S, times our thermal conductivity value K, times right here the difference between those 2 temperatures at the 2 isothermal surfaces, T1 minus T2 right there. Now, if we want to find some exact and approximate results for common 2D and 3D dimensional systems, we can reference our table 4.1a in our textbook. So now going to table 4.1 in our textbook right here, what this table for part A has right here is we have our conduction shape factors and dimensionless conduction heat rates for these selected systems. For part A, again, this is our shape factors right here. We have this relationship we saw in that previous equation right there, that Q is equal to our shape factor S times our thermal conductivity K times that temperature difference between our isothermal surface temperatures right there of T1 minus T2 right there. So that's that governing equation we just saw before. Now there's a bunch of different cases for this here, but there's 11 different cases that we can look at for this table 4.1a right here. So for case 1, we can see over here they tell us exactly what the case is. They give us a schematic for that, tell us what the restrictions are for that particular case right there, and then where our relationship, our equation is for our shape factor. So let's just take a look at this first one right here. We have an isothermal sphere, so it's a sphere buried in a semi-infinite medium right there. So those are things as we're solving out problems that we want to look for in the problem statement. Things they might say, is it a sphere? Is it a pipe? You know, because that's the difference right here between our case 1 and our case 2 right there. Are we dealing with a cylinder or are we dealing with a sphere? Well, looking at this diagram here, it's hard to tell. It just looks like a 2D end right there, but this really is a sphere right here, buried in a semi-infinite medium right there. The restrictions are here, our Z, which is our depth from our surface right here down to the center of the sphere right here, needs to be greater than D over 2, or our diameter divided by 2 in order for this to hold true. And if that is true, then we can use the shape factor over here. This is 2 pi times that diameter of our sphere right there, divided by 1 minus D, the diameter, all divided by 4 times Z, that depth to the center of our sphere right there. So this, again, is something that we have a problem statement. Maybe it's a schematic, maybe it's a word problem, a combination of both. We double check that it fits what case best out of all these different cases right here, and make sure we are within the restrictions as well. And if that's the case, we can back out our shape factor equation. So again, let's take a look at the second case here now as well. So this case 2 right here talks about the horizontal isothermal cylinder of this length L. So we can see there's our length L right there, our cylinder right there, buried in semi-infinite medium right there. So there's our depth to the center of our cylinder right there. It's a Z right there. There's our isothermal surface temperature right there, T2, and there's the surface temperature of our buried object right there, T1 right there. And we can see it has some diameter D right there. Now, there's two different cases. The restrictions here that said if our L is much greater than D, so the length of our cylinder right here is much greater than the diameter, then we can use this relationship right here, where we have 2 pi L over the inverse hyperbolic cosine of 2Z over D right there, where Z is that depth again, D is the diameter, and L is our length of our cylinder right there. Or if we have the case right here where L is still much greater than our D right there, and we have that Z is greater than 3 times the diameter over 2, then it simplifies down to this relationship here. What we can see is every case tells us that we need to have our L much longer than our D for it to be considered for this case 2 here for the cylinder right there. And then there's two different cases within that L being greater than D. And the case right here, second case right here, is when that Z right here, our depth from the surface right there where T2 is greater than 3 times our D over 2, our diameter over 2. So this continues on for several different cases. We can see it for a vertical cylinder in a semi-infinite medium. We can see it for conduction between two cylinders. So this is a case where we have two different cylinders buried right here of length L and a infinite medium right here. So then we have this case and a slightly more complicated shape factor. And then we continue on. Let's take a look at some other cases as well. So we continue on to case 5 right here. So this is where we have a horizontal circular cylinder. And then case 6, we have a circular cylinder of length L centered in a square solid of equal length right there. So this is a very special case right there. It can reduce down to this right here. And then case 7, we have an eccentric circular cylinder of length L in a cylinder of equal length right there. So we have this case here. So this is where we do really want to pay attention. You know, maybe multiple cases will fit our scenario based upon our word problem for the problem statement and our diagram, but is there a better fit that we could use? If they're looking between two of them, well, it kind of fits this one, but it's actually a more specific case like this. Let's go with this case instead. So then we continue on with the last 4 cases right here. So we can see conduction through the edge of adjoining walls right here. So this is a great one for structures right there. Maybe we're talking about a corner down here in case 9, or a disc down here of a known diameter right here. Sitting on top right here of our semi-infinite medium of thermal conductivity K and temperature T2. So that's a completely different situation than we've seen yet. Or we just might have a square channel of some length out here. So these are all the different cases that our book presents, and there's even more and more that we could use there. And that's where also if one of these simple geometries doesn't fit, then maybe we do need to think about doing some of this finite methods, these different numerical solvers for these types of problems. But for this right here, these are the 11 cases that were presented in part A of our textbook. So let's just say we did have a problem right here, and we had this case right here that's related to case 6. So we have a long circular cylinder centered in a square solid of equal length right there. So we can see, okay, there's our equal length right there of W right there. There's our diameter of our cylinder right there, and it's going to be a long, which means the L is much longer than our W right there. There's our T1 and our T2 temperatures right there. So if this is the case for the problem that we have, then we can use this shape factor right here that we looked up from that table 4.1a right there. So our shape factor S is equal to 2 pi L, where L is the length of that circular cylinder right there, divided by the natural log of 1.08 W right there, which is the, again, this is a square, so this is the length and the width of that square right there, divided by D, which is the diameter of our circular cylinder inside of that square. Not only inside it, but centered inside of that square as well. So we know the location center of this is going to be W over 2 right there. Now we can take a look at our two-dimensional conduction resistance right here. So this relates back to our next equation in our textbook right here, which is our 4.21, which involves that S value right here that we either looked up from a table or got from this equation 4.20 right there. So we can plug that value in once we have it there, multiply that by our thermal conductivity K. And again, this is for constant thermal conductivity problems right there. Take the inverse of that, and what this is going to give us is this is going to give us that two-dimensional conduction resistance right there. So you can see there's our R for conduction resistance right there. So there's our conduction, and we have a 2D right there. So our subscripts are important when we're looking at these variable names to know exactly what we're looking at. Now next I want to take a look at the dimensionless conduction heat rate. So for this here, what we're looking at here is isothermal objects of surface area A sub S and temperature T1. This is embedded in an infinite medium that has a temperature of T2, and the heat transfer then be represented by a dimensionless conduction heat rate, which we're going to call our Q star right here, SS right there. So this is our dimensionless conduction heat rate right there, and this relates back to our equation 4.23 in our textbook right there. So our Q right there, our heat rate there, is equal to this Q dot, or our Q star SS, times our thermal conductivity K, times the surface area AS, times that difference in temperature, where T1 is the temperature right here of the isothermal object, and T2 is the temperature of the infinite medium right there. So it's T1 minus T2, all divided by the length here of our L sub C, where L sub C is represented by equation 4.22, and this is the object's characteristic length, or L sub C, C for characteristics. So again, these indices are important for what we're determining, what we're calculating here. So our L sub C is given to us this relationship right here of our AS, or that surface area right there, divided by 4 pi all to the 1/2 power. And this again relates back to equation 4.22 in our textbook. Now again, there's another table that we can look at when we're dealing with these dimensionless conduction heat rates, and this is for the exact and approximate results for some common systems. These are provided in our table 4.1b. So now if we go back to that table 4.1 in our textbook here, now we go to part B right here, we're looking at the dimensionless conduction heat rates right here, and this is our governing equation that we just saw earlier right there. So we have our Q is equal to our Q star SS times our thermal conductivity K times that surface area A sub S times the temperature difference all over L sub C, where L sub C is equal to our AS divided by 4 pi to the 1/2 power. So this is great. This table not only gives us these cases right here in 12 through 14 for these different shapes, but also references the governing equations that we just discussed on the previous slides. So let's just take a look at a couple of these right here. Case 12, you have an isothermal sphere. Case 13, you have an infinitely thin isothermal disk. Case 14, we're looking at an infinitely thin rectangle with some length L. And case 15, we're looking at a cuboid shape of height D with a square footprint of width D right there. So these are some relatively specific cases. We can see we have a schematic of what these look like. Then we have what our active area is. So this is important for calculating our AS. So now we have a relationship for what our AS is for each of these as well. And then from there, we also have this Q star SS value right there. So we can take these values for whatever these are, plug them back up in here for our Q star value right there, and then we can plug in for our AS value all of these relationships here, and for our AS value right there, as well as right there, plug those back into those governing equations, and we can do that to get our L sub C, to plug our L sub C into this relationship there, to then get our Q value right there from that first equation. So let's take a look at this for a specific case here. So we're going to look at case 12 right there, the top one from that table 4.1b. This is an isothermal sphere right here, so we can get our information from that right there. We can get our Q star SS right there is going to be equal to, this is our dimensionless conduction heat rate again, equal to 1 from that table right there. So for any object right there, we can say we have this relationship right there, that our Q star SS right there is approximately equal to 1 right there. So then we can plug that back into the other equations. We can plug back in for our A sub S to get our, again, our L sub C, plug back in our L sub C up here in order to back out our Q value right there, where again, we plug this QSS in right to that point right there. So now let's take a look at an example problem. So here we have example problem 4.9. In this problem, it tells us that radioactive wastes are temporarily stored in a spherical container. So now we know it's a spherical container right there, and the center of which of this spherical container is going to be buried a distance of 10 meters below the surface right here. So we can see that right there. There's our spherical container right there. There's our distance right there of Z is equal to 10 meters right there. And that's below the Earth's surface. There's our top surface right there. So the outside diameter of the container, they tell us, is 2 meters. So there's our capital D is 2 meters. And 500 watts of heat are released as a result of radioactive decay right there. So that's some information we can see right there. There's our EG dot right there, 500 watts right there. And we zoom in on a radioactive spherical container right there. Now they tell us now if the soil surface temperature right here is 20 degrees, so there's our T2 of 20 degrees Celsius right there, they're asking us now what is the outside surface temperature of the container under steady state conditions. So this is a little bit different than we've done before. So rather than solving for our E sub G, we have this E dot sub G right there, and we need to work backwards in order to get our T1 right here. So the first thing that we want to do is take a look at the problem statement and the initial given diagram, and from there create our setup page. So this right here, this is problem 4.9. What is given to us? So in the given information right here, we have our Z is equal to 10. So this is equal to 10 meters right there, and this is our buried depth. So again, 4 things that we want to include in here. We got the variable, we got the numerical value, we have our units, and we have how it relates to our physical problem. So there's our variable Z. There's our numerical value of 10, there's our units of meters, and here's how it relates to our physical problem, our buried depth right there. So this is Z is equal to 10 right there. We can draw out our simplified diagram over here, and we can see that, okay, there's our Z is equal to 10 meters to the center of that sphere, buried sphere right there. Then we have D is equal to 2 meters, which is the outside diameter of our sphere right there. Then we have our T sub 2 is equal to 20 degrees Celsius. This is the soil surface temperature right there. And this I convert right to Kelvin, 293 degrees Kelvin right there. Then we also have our K value right here. Now our K value was 0.52 watts per meters times Kelvin. Now this was not directly given to us in the problem statement. This was something that we needed to look up from our table A3 in our textbook. So we'll take a reference on that, and this will be look up for soil at 300 K, which is approximately what we're at right there. And we're going to do this from table A3 in the back of the book. Now, the other thing that they ask us to do here is find the outside surface temperature of the container, which is our T1 right there. So we can zoom in on this right here. There's our T1 right there. There's our Q going out right there. There's our E sub G, E dot sub G right here that's given to us in the problem statement. It's 500 watts right there. So we have all of our given information, our given diagram right there. Now the next thing we need to do is write out our assumptions. So we're going to assume steady state and that the soil is homogeneous with constant properties. Now to get that thermal conductivity value for our soil, we go to table A3 in our appendix right here. So this is on table A3 right there. This is for other materials. So we go through, there's a lot of different materials listed under other materials. We go to the bottom, we can see there's soil right there, which is what we're dealing with in our problem. This was listed in our problem statement right there. So now we go down to our temperature here. This is at 300K. We're pretty close to 300K right there. So we go over here to our thermal conductivity value, our K value right here in watts per meters times Kelvin, which we're looking for, and that's when we see that we have this 0.52. So that's where we got that value there for our K value for this problem there that we saw on our setup page. So now if we take a look at our schematic or given information from our problem at the beginning here, what we can see is we have this, okay, we have a spherical container and we have this known depth Z right here of equal to 10 meters. We have this diameter here. So this right here, if we go to our table 4.1 that we talked about earlier in this module right here for our conduction shape factors and dimensionless conduction heat rates for selected systems right there, then what we can do is we go to part A right there for our shape factors that we're looking for right now in part A. What we can do is we can say this is closest to our case 1. We go through all 11 of those cases and we find out this is the closest one. We're dealing with an isothermal sphere buried in a semi-infinite medium. That's exactly what we have up here in this problem statement right there. So now we can take a look and we say, okay, now is Z greater than D over 2? This is our restriction. So this is something that's important right there. So our Z is 10. Is that greater than D over 2? Well, D is 2, so 2 over 2 is 1. Is 10 greater than 1? Yes. So we're okay. So therefore, based upon this information, it's case 1. We meet the requirements right here, the qualifications. So this is our shape factor right here. So our shape factor S is equal to here 2 pi d divided by 1 minus d over 4z right there. We have all those. We have our d value and we have our z value that we can plug in to get a numeric value for this. We should then plug back in up here for our S right here into our Q equation right here for this problem. So now that we had the opportunity to read through the problem statement, look at that initial given diagram, and create our setup page, we listed out all of our givens, all the things they're asking us to solve for, all of our assumptions. Then from there, we went on to our tables and our appendices to get our values for our shape factor. So now what we can do with all that information is begin our solution. The first step in our solution is to determine our governing equation. Well, our governing equation, we can go back to that setup page, look at what they give us, we're asked to solve for, come up with a general governing equation right there, which is going to be our energy balance on the container. So if we recall, we have this general equation here that our E in minus our E out right here is equal to E sub G right there. This is our inflow minus our outflow is equal to our energy generation, or E dot G right there, which is also equal to, for our problem right here, our Q value right there. So now we can go to equation 4.20 in our textbook right there and take a look and say that Q is equal to our shape factor S times our K value here, thermal conductivity, times the difference in our temperatures right there. So that's our T1 and our T2 right there. So this is our general governing equation that we're going to use for our Q value, which we can then use to our Q value is our E sub G, E dot sub G right here, our energy generation that was given to us in the problem statement, so that can be plugged in for our Q value there. We can look up our shape factor. So for our shape factor, we can go to that table 4.1 right there, and that's what we just did previously, and we saw that this was case 1. So we have this value right here, that S is equal to 2 pi d divided by 1 minus d over our 4z, and this is for an isothermal sphere buried in a semi-infinite medium, which is exactly what we have occurring for our problem there. So with this here, now we have our S value right there. We can plug this S value back in up above here for our governing equation from 4.20 in our textbook right there. So when we do that, what we end up with is that Q is equal to 2 pi d over 1 minus our d over 4z, which there's our shape factor S right there, times our thermal conductivity K, times that temperature difference right here of T1 minus our T2. So what we can do is we can take that equation from our previous slide right there for Q right there, bring it over, have it boxed in up top here. And what we want to do is rearrange this and solve for our T1, because that's what we're asked to solve for in this problem right there, the temperature on the outer surface of that sphere right there. So if we want to solve for that T1, what we want to do first is we kind of take this shape factor right there and our K value and divide it over on the other side here. So that's what we do here. So now we have Q divided by that 2 pi d over 1 minus d over 4z right there times the K value right there. And this is equal to our change in temperature, our T1 minus T2. Now if we want T1 by itself, we can add the T2 back over to this side. So we're left with T1 is equal to T2, plus we have here the Q over K right there as we rearrange and pull those out of that relationship there, times now 1 minus d over 4z divided by 2 pi d there. Now we have some known values. We know our D value, we know our Z value, we're given our Q value, we looked up our K value, and we have our T2. So we can start plugging in our known values. When we do that there, we say T1 is equal to our T2, which was given to us as 20 degrees Celsius, times now right here we have our Q over K. Well, our Q was given to us in the problem statement right there, so that's our 500 watts right there, divided by our K. We looked that up, so our K value was 0.52, and that was for our soil at 300 degrees K. When we looked it up in the back of the temperature of our book, back table in our book right there. Now we have this is in watts on the top, on the numerator, and on the denominator we have watts over meters times Kelvin right there. Pay attention to our units there. Now we can plug in 1 minus our D is 2 meters. Our Z times 4 would be 40 right there, and units of meters right there. Meters and meters cancel there. So we can take a look and we can see our meters will cancel there and there. So what we're end up with at the end is we have it in value of temperature right there. So let's go to the bottom, 2 pi times there's our 2 meters right there for D. We end up with, when we plug this all in, just left with temperature on the bottom right here. So we left with now a value of T1 is equal to 92.7, and this is in units of degrees Celsius. So pay attention to units, make sure you do the conversions correctly right here. But that's what we end up with now for T1 is 92.7 degrees Celsius. So let's take a look at another example problem here. Let's take a look at example 4.32. So this problem references back to chapter 3 when we're dealing with fins right here. We'd say that when in chapter 3, well, we assumed that whenever fins are attached to a base material, that the base temperature is unchanged. But in fact, what happens is if the temperature of the base material exceeds the fluid temperature, attachment to the fin depresses the junction temperature, our T sub J, below the original temperature of the base, and the heat flow from the base material to the fin is going to be two-dimensional. So that's what we can see going on down here. We can see the heat flow from the base to the fin down here in our diagram right there. And there's that T sub j right there, that junction temperature that we talked about right there at the junction between the base and the fin right there. So now what they ask us to do here is they want to consider conditions for which a long aluminum pin fin of diameter given to us as D is equal to 5 millimeters is attached to a base material whose temperature far from the junction is maintained at a T sub B is equal to 100 degrees Celsius right there. And the fin convection conditions correspond with an H value is equal to 50 watts per meter squared times Kelvin, and our T sub infinity is equal to 25 degrees Celsius. Now, with all that given information, we can reference back up here. There's our aluminum pin fin. Here's our aluminum or stainless steel base down there, depending on which problem we're dealing with for this diagram right there. Now, with all this information, we have three different things they ask us to solve for. So in part A, let's look at that first. They say is what are the fin heat rate and junction temperature of when the base material is at I aluminum, K is equal to a 240 watts per meter times Kelvin if we're dealing with aluminum, or stainless steel. So that's why we say here this is either aluminum or stainless steel with that right there, with a K value of 15 watts per meter times Kelvin. So for part A, we want to find the heat rate for the fin and the junction temperature for two different types of base materials, an aluminum and a stainless steel, both of which they give us our thermal conductivity for. Now in part B, they say now they want us to repeat the foregoing calculations if a thermal contact resistance right here, our double prime indices of T comma J, for that right there being our thermal contact resistance right there, given to us as a value of 3 times 10 to the negative 5th meters squared times Kelvin per watt right there, if this is associated with a junction of joining the pin fin to the base material right there. So this is saying there is going to be a thermal contact resistance between the pin fin and our base material right there, and they're giving us a value for it. So we're basically going to repeat part A, but now considering this as well. In part C, they're saying, okay, well now considering the thermal contact resistance, go ahead and plot the heat rate as a function of the convection coefficient over the range, for H value for our convection coefficient right there, from 10 all the way up to 100 in units of watts per meter squared times Kelvin for both of these different materials. So with this problem, we had quite a bit of information given to us in the word problem, and even the diagram had quite a bit more information for us there, and we had 3 parts that they asked us to solve for in our solution. So this is one that we really definitely want to take our time and create a good setup page so we clearly understand everything that we were given to, everything that was given to us in the problem statement, everything that we're going to be solving for, and what the assumptions are we're going to make. So that's what we do there. This is for problem 4.32. Here's our given information right there. So again, 4 things in our given information. We have our variable name with our indices right there, our numerical value, our units, and how it relates to our problem. So this is our base temperature right here. This is T sub B for our variable. It's 100 units of degrees Celsius right there. So we can convert that to Kelvin right away just in case we might need it. 373.15 Kelvin. Then we do the same thing for our surrounding temperature. Our T sub infinity right here is 25 degrees Celsius, which is equal to 298.15 Kelvin. And we have our pin fin diameter right there, which is our capital D, which is 5 millimeters. If we convert to meters, this is 0.005 meters. And we have our H value given to us here now as 50 in watts per meter squared times Kelvin right there. I redraw a simplified version of my diagram right here. Well, there's my contact resistance there. There's my temperature in my base. Here's my aluminum pin fin right there. And here's my surrounding temperature out here. So my contact resistance here, my R double prime TJ, is equal to 3 times 10 to the negative 5th in units of meters squared times Kelvin per watt. Then I have my K value for my aluminum right here, if I'm dealing with aluminum right here. And this is 240 watts per meters times Kelvin. And I have my aluminum value for my stainless steel as 15 watts per meters times Kelvin. So pay attention to our indices for aluminum, sub AL. For stainless steel, it's a sub SS right there. Assumptions. So what assumptions are we going to make now that we have all of this given information in front of us here and we know what they're asking us to solve for? Well, we're going to assume a steady state conduction. We're going to assume constant properties, and we're going to assume, based upon the way they word the problem, it's going to be an infinite pin. So with that information on our setup page there of everything they give us and what they're asking us to solve for, our next step as we begin our solution is to start with our thermal circuit right here. So first off, we're dealing with this for part A right here, where there's no contact resistance. So we're going to draw our thermal circuit with no contact resistance right here first. So this right here, we have our T sub B. So there's our diagram right there. So T sub B is at the base right there. Then we have our T sub J at the junction right there. Then we have our T sub infinity out here as our ambient temperature out here. So we draw that in. There's our circuits right there, T sub B, T sub J, T sub infinity right there. So this is resistance R sub B right there and R sub F right there, where R sub B is the resistance of the base as we get up to that junction right there, and R sub F is the resistance through the fin right there. So this is our thermal circuit for no contact resistance. Well, in part B, we asked to consider contact resistance right there, so we can draw that into our thermal circuit as well. So then we still have our T sub B right there and our resistance through the base, our R sub B there. Then we get to our junction. Then after the junction right there, there's our contact resistance right there, R sub T comma J right there, contact resistance. Then we get up here now to our fin, so we have our R sub F there, and then we get out to our temperature right here of our T sub infinity right there. So now what we want to do is look for our governing equation. So we can go to equation 4.21 on page 235 of our textbook right here for resistance for our 2D conduction right there. And again, we're looking just right now at our base first. So we can see, okay, we have our R sub T right there, our resistance right there for conduction for 2D right there. And this is given by the relationship of 1 over S for our shape factor right there times our thermal conductivity K, where for our base right there, our shape factor for this relationship is going to be 2D right there. And where this comes from is this is case number 10. So if we go back to that table 4.1 on page 237 of our textbook, we can take a look at case number 10, and that's where we get this value for our shape factor for S right there. So we can plug that in above there. What we end up with, the resistance of our base materials is equal to, R sub B is equal to 1 over, we plug in for that shape factor of 2D times our thermal conductivity K right there. And you can see I have a subscript here for base. This is the conductivity of the base as well. So here is our table 401. So this is the case we want to for case 10 right here. So case 10 right here is a disk of some diameter D right there and temperature T1 on semi-infinite medium or thermal conductivity K and temperature T2. So this is kind of the situation we have here for fin. It just comes out a little bit longer for this case right here. So that's where we get our shape factor right here of 2D. And why it's okay that it comes out longer is because if you look at our restrictions, there's none. There's nothing saying, according to this right here, that we can't use this relationship, even if this pin comes out further, which would exactly be the case that we have. So for the next step in our solution, what we want to do is take a look at table 3.4 on page 161 of our textbook for a fin. So if we look at the top title here, here's table 3.4 right there, and here's the temperature distribution and heat loss for fins of uniform cross section. Now, does this apply to us? Yes, that's exactly what we have. So again, that's something we want to do. We really want to pay attention to what we have. We can't just blindly go to these tables and pull stuff off, but we have to make sure that it matches our case. So really take a look at the definition of these tables and the cases and make sure it fits with our problem. So then there's 4 different cases over here, A, B, C, and D. Well, we don't really apply to case 1 for convection heat transfer. It's not really adiabatic. We don't have prescribed temperature, but it is an infinite fin down here. So we can see, we can go over to equation 385 right here for the fin heat transfer rate, or Q sub F right there, and this is equal to M. So now we come down here and say, okay, for the infinite case right here, for infinite fin, case D, we have Q sub F is equal to M, where M is given at the bottom of the table right there. So M is equal to the square root of H times P times our thermal conductivity times our A sub C times our theta B right there. And this right here is all under the square root of that. Theta B is on the outside right there. So that's what we write down here. M is equal to the square root of H times P times A sub C times K right there times our theta term, where our theta is given by this relationship here, T minus T infinity. So theta is equal to T sub B minus T infinity right there for our case, temperature of the base and the surroundings. So we plug that back into this relationship here, that Q sub F is equal to M from equation 3.85. We have that Q sub F now is equal to the square root of H times P times our A sub C times K times our T sub I minus T infinity right here. So now from our heat rate equation for thermal circuits, we have the relationship here that our Q sub F right here for our fin is equal to our change in temperature, our delta T, over that resistance R. So here's our thermal circuit right here for no contact resistance right there. We have a temperature of our base right there, T sub B, temperature of our junction, T sub J, and our temperature of the surroundings, T sub infinity right there, where that's the resistance across the base, that's the resistance across the fin. So from our junction to the surroundings right there, that's the pin right there, on that section right there, we have the Q sub F right there for our fin is equal to the temperature at the junction minus the temperature of the surroundings over that R sub F value right there. So that's to get from there to there for our fin right there. So we can see now we have 2 expressions for our Q sub F, and we can set them equal to each other to eliminate that Q sub F and solve for the variables. So that's what we do right there. So we have this relationship, our T sub J minus T sub infinity, all over our R sub F. This is equal to our other value for our Q sub F right there, the relationship, the square root of our HPACK, all square root of that right there, times our temperature difference right there. So now we can take a look at these and say, well, I can subtract this and solve for R sub F. So I can say, well, there's my T sub J minus infinity, there's my T sub J minus infinity right there. So what I have right here now for this relationship here is these two cancel out, so I have 1 over this. So R sub F is equal to 1 over the square root of H times my PACK right there. Well, I can also rewrite that as R sub F is equal to HPACK to my -1/2. Just another way to write that there, where let's calculate and see what we can find. What do we know? What can we plug in for everything here? Well, my p-value here is going to be equal to our pi times d right there. So our pi times our value for d is 0.005 when we convert to meters. So I can plug that value in right there for my p-value right there. And my a sub c right there for area is pi d squared over 4. Again, I have my d value there in meters of 0.005. We can get that back from our setup page, divided by 4 right here, so we can plug that in. And what we end up with for this value for a sub c right here is 1.96 times 10 to the -5th right there. So I can start plugging in my knowns to this equation up above here. So I have an H value of 50 in units of watts per meter squared times Kelvin. Then I have my P value right there, which is my pi times my 0.005 meters. Then I have this over here now for my area of pi times 0.005 squared over 4. And then I have my value right here for my K value for thermal conductivity right here for the aluminum fin. And that's for 240 times my watts over meters times Kelvin right there. So for this here, you notice I haven't simplified anything down because some things canceled out. I'm going to do some unit analysis. I'm also going to see there's also values that are going to cancel out with the squared here and my meters there and my everything else. So I can cancel out my units and do a unit analysis and double check that to make sure it's correct. And when I plug that all in, my units do come out correct. We have a K per W right there, which I would expect for my resistance right there for thermal resistance. And this is a value of 16.4. So now I have this value for my RF that it has to solve for right there. So now if we want to consider contact resistance, we're given this value right here that our contact resistance at the junction right there is 3 times 10 to the -5th in units of meters squared times Kelvin per watt right there. Therefore, we can plug this relationship in and say, well, our R sub T J, this is going to be per area right there. So divide this by our A sub C right there in order to get the resistance right there. So we can plug this in as our 3 times 10 to the -5th. Double check your units. This is why we're able to do this here. Get this in the correct units. This is in meters squared times Kelvin per watts right there. And this right down here in our A sub C is equal to meters squared. It's an area. It's squared right there. So the meters squared canceled with our meters squared right there. And again, this was pi times 0.005 meters squared over 4 right there. So our units were meters squared and meters squared canceled. We're just left with K per W, which is exactly what we want for this right here. We do out our math, and our contact resistance or our thermal resistance right there for that point right there is going to be a 1.528 in units of Kelvin per watts right there. So for our base conduction resistance equation now, we have this R sub B is equal to a 1 over 2D times K sub B that we saw before. Now we can plug in our known values right here. So if we plug in our known values right here, we can solve for this R sub B for aluminum and for stainless steel. So that's what it asks us to do for both materials. So I'm going to do this simultaneously right with each other as we go through this. So there's our general governing equation right here for base conduction right there. So we can say R sub B is equal to 1 over 2D times our K sub B. So 1 over 2D doesn't change between either of these, but my K value does change right there. So for aluminum, it's 240 watts per meters times Kelvin, and for stainless steel, it's 15 watts per meters times Kelvin. So now we get an R sub B for aluminum, which is 0.417 K per W, and for stainless steel, it's 6.667 K per W. So from there, we can now calculate the total thermal resistance for both the aluminum and the stainless steel bases, which would ask us to do it for both, with and without contact resistance. So all that first part was to get all those values so we can come in and calculate it for all those scenarios right there. So we have our governing equation right here. We have our Q sub F is equal to our difference in temperature from the base to the air. So now through the whole thing, all the way through the base right there, divided by our total resistance. Now our total right here, this value will vary with the two different base materials and also with and without contact resistance. So we're going to have different values that we need to plug in for this right here, depending on what base material we're dealing with and if we're dealing with or without contact resistance right there. So now what we can do is we can say that our T sub J right there, our temperature at our thermal junction right there, is equal to our surrounding temperature plus our Q sub F for the fin right there, times now our R sub F times our R sub T sub I right there for those resistances, and that'll be our equation that we can start plugging into. So we can plug into that there, and I think the best way to represent this is a little table right here. This could be in Excel, or you could do this in MATLAB or Python, something like that. But right here, even just by hand, our T sub j is equal to that surrounding temperature plus our Q sub f plus those two resistances right there, R sub f and R sub tj right there. So yielding the following results. So again, we have different cases right here. We have a base, two different types of bases right here, and we have two with and without contact resistance right here. I figured this is the best way to represent it right here. So our R sub b for the two different bases, we've calculated 0.417 for aluminum and 6.667 for stainless steel. And up here on the top right now, we have with and without our thermal resistance right here. So if we're dealing with aluminum, our Q sub F, if we plug into that right there, for our base without thermal resistance, that's why this chart is nice right there. We can go down and down right there. So aluminum base without contact resistance right there is 4.46, and our T sub j temperature, junction temperature right there is 98.2 in Celsius. Then if I wanted to come over here and do it with, then I can rerun that calculation, plug back into this here. And again, did this in MATLAB or even Excel, you can write a little formula that automatically calculates this and have a list of all these different values you can plug in and alternate through. But we have here for our aluminum right here, we have a Q sub F of 4.09, and we have a temperature at the junction right here of 92.1. So this is also a great way to compare these with and without our contact resistance right here. How do these change? Well, our Q sub F goes down, as does our temperature. So now if we deal this with stainless steel, again, now we're using this R sub B when we go up here, we go back to our governing equation right here. So without contact resistance for stainless steel, we have a Q sub S value right here for our fin of 3.26, and we have a temperature of 78.4. And with contact resistance, it drops down our Q sub F to 3.05 and drops that temperature down right there to 75.1. So again, this table is a great way to look at it all, compare it all at once, and also a great way to calculate it, again, if you're using MATLAB or Excel to create this.